or material removal process. So under that, we have seen how the chip is forming during machining process. That means material ahead of the tool tip will be compressed and it is subjected to high pressure and stress. So because of that, it will be, go to plastic state, and after that, shearing, yielding. Yielding of the material will take place after plastic deformation. After some time, material will yield. Okay, so after yielding, we are getting shear force. That shear force is removing the material from the workpiece. And we have different types of chips. What are the types of chips that we have discussed? Names. Please respond. What are the types of chips? Names of different chips.
Sir, continuous chip, discontinuous chips, built-up edge.
Yes. So first one was a discontinuous chip, then continuous chip without built-up edge, continuous chip with built-up edge, then serrated chip. Okay, and we have seen the favorable conditions for the formation of various chips. And we have seen how to, what are the advantages or disadvantages of various forms of chips. And we have also discussed the conditions for the elimination of this built-up edge formation, okay, or reducing the built-up edge formation tendency. So under which conditions and what conditions the built-up edge formation is less. Okay. Now let us discuss the next subtopic, that is chip breakers. So we have understood that in many cases, okay, in many machining operations, the type of chip formed is continuous chip in general, because during machining, so most of the hard materials also will act as ductile materials. Now how? Because the material ahead of the tool tip, okay, just ahead, okay, we are going to cut it immediately. So that is subjected to compression, and due to that, okay, compression, then finally it will be going to the plastic state before it is being cut. Okay. So during that process, the material ahead of the tool tip will be heated to some extent. So that heating will make that material little bit soft. So even though the material is hard at room temperature or at the normal condition, so during machining, because it is subjected to some amount of heat, okay, it will act as ductile material. Okay, its hardness will decrease definitely for any material. So in general, okay, most of the materials will act as ductile materials. So because of that, we'll get continuous chips, or at least chips, serrated chips. Okay, getting discontinuous chip is not okay, regular phenomena in machining. Okay, for very brittle materials, you will get that kind of discontinuous chip. So now if the chip is continuous, so we have some associated problems with that, because okay, cutting tool is getting heated up too much and it will deform later on, and the chip, long chip that is coming out may harm the worker, and it will also disturb the surface finish of the machined portion, and chip disposal is also difficult, okay, because you are dealing with very long chip curled in different directions, and okay, you cannot handle the long chips, and okay, you have to take those chips away from the machining area, you have to dispose. So disposal is also a difficult thing. So for all these reasons, and of course, yeah, mainly these. So because of all these reasons, uh, okay, we prefer small chips. But only problem with small chips is okay, there is no uniform force during machining. That is the problem. But otherwise, so formation of small chips is advantageous. So for that, we okay, we'll try to break the chips intentionally because they are not naturally breaking many times. So you have to make some arrangement to break those chips. Okay, you have to cut that long chip uh, into small chips during machining itself. Okay, you are not taking the chip and cutting it later. During machining itself, a small chip should form and it should fall, and it should be easy for the operator to deal with that. So further, we have to make some arrangements on the cutting tools. So now let us see what are the different types of chip breakers. So we have discussed up to this portion previously. If you have different types of chips, so what is the surface finish? If it is discontinuous, irregular surface finish. If it is a continuous chip, you will have good surface finish. If it has built-up edge, some portion of the built-up edge is sticking on the surface again, surface finish will be poor. Now need for chip breaking. So why do we need to break the chips? I have already discussed this, but let us quickly see these points. Now it is essential to break continuous chips because of the following reasons. Safety of the working people. So if the chip is very long, okay, it will come and hit the operator, or it will cut the hands or fingers of the operator. Okay, those are the problems. Now prevention of damage of the product. Okay, to prevent the damage to the product, because once it is machined, its surface should not be disturbed. But if your long chip is there, okay, it will be coming in between the tool and the workpiece, and it may damage the surface finish of the machined component. Now, easy collection and disposal of chips. So, handling this long hot chip, okay, which is sharp also, is difficult. So, better to break it and dispose it. Now, methods of chip breaking. So, how do you break the chips? So, one is breaking. So, self breaking means a chip is breaking by itself, and you are not providing anything extra on the cutting tool to break the chip. Now, the other one is forced chip breaking. So, you have to force the breaking process, chip breaking process. You can do it by additional tool geometrical feature, that is one thing, or some additional devices. Now let us see these. So first is self breaking of chips. So first you can see figure A, that is a natural chip breaking. Now chip is being cut and it is coming and hitting the rake surface of the cutting tool, and now it is like chip is like a cantilever beam if you observe. Okay, so chip is flowing in this direction and it is hitting this. It is like this almost. Okay, it is like a cantilever, okay, not a straight beam, but it is in that shape. So once it is coming and hitting here, it has to change its direction, so it will bend. So while it is bending, some what is happening is strain hardening will take place, or work hardening, you will say. Okay. So, and of course, it is being heated up also. It is compressed, strain hardened, and it is getting heated up. So those are the things. So once this chip is moving a little bit away, so now it will start cooling immediately. So due to cooling, so there will be some residual stresses coming, okay, in the chip, and due to the self weight of the chip also, it will break at different locations, okay, at some location. That is natural breaking. So during cutting, the chip is subjected to high temperature and high stress also. Stress means due to strain hardening. So due to that, and whenever it is going away, a little bit away from the tool, it is trying to cool. And during that period, and due to the self weight of the chip also, okay, wherever it is weak, it will break automatically. That is natural breaking. So we are not doing anything here. It is naturally happening. Now the second is striking on job. Okay. So first one is, it is just naturally breaking. It is not even striking the job. Okay. Second, so same thing. Chip is coming here and hitting the tool. Now it is going here. Even then also, if it is not breaking, let us say in some conditions, because all the chips will not have the same properties, all the materials. So some of the very ductile materials may not break due to this strain hardening, etc. So in some cases, the chip will curl like this and hit the workpiece. It is hitting the workpiece. So, and due to that, some stress will form here at some location, and it will break. So this is how the chip is breaking, by hitting the workpiece here. That is one thing. Now the next is striking at a tool flank. So particularly in oblique cutting, so chip is coming out and it is curling in different directions. It is coming and hitting the flank surface. Okay. So whenever it is hitting the flank surface, it is forcing against the flank surface and it will break. So these are the different ways of self-breaking of chips. Is it clear?
Yes, sir.
Okay. Thank you. Then, actually, one point I have not discussed earlier is, why do chips call? Okay. In the ideal case, or one may think that it should come out straight. Why is it calling chip? Any reasons that you can think? Why do chips call? Why they are not coming out straight? Because of curling only, these self-breaking is happening. Otherwise, it will not happen. There are many reasons. One is, as we understand that during cutting process, the chip is getting heated up. Okay. And one side of the chip is in contact with the cutting tool, and the other side is subjected to natural air. Okay. So the one side will cool faster, okay, which is not in contact with the tool. Okay, it is freely subjected to the flowing air outside. So it will cool quickly. the other side will will take more time for the cooling to take place. So there is non-uniform cooling on either side. So once it is cooling here in this side, so it will contract. Okay, contraction will take place on that side. The other side, it will not contract quickly. There is a variation. So naturally, the chip will bend or curl due to that. Okay, so that is one reason, main reason. The other one is also on one side, the chip is in contact with the workpiece. There is a friction between the chip and workpiece. The tool is trying to push this chip towards the workpiece, and whereas chip is trying to move away, and there is some friction and some sticking action is also there. Due to that, the one side, the back side of the chip will not move fast. Okay, it will move slowly because it has to overcome the friction between the chip and the tool. Now, whereas the other side, it is free to move actually. Okay, so the chip will deform due to the friction and the heat. Okay, on the back side, it is in contact with the workpiece. So velocity is also not same. Understand? There is varying velocity on either side. So that will also make the chip to curl. Understand? On this side, it is trying to move fast. On this side, it is. But ultimately, once only one side is trying to move fast, the other side will move slowly. But the entire chip has to move at the same time only. Okay, one side cannot go, and there is no slipping taking place here. Understand? So due to that, the material here is compressed because it is trying to move fast, but it cannot. So what is happening is compression of the material is taking place here within the chip also. So whenever there is a compression here, so it will automatically coming close, or it is trying to call there. So these are some of the reasons. There are few more reasons, like when you are providing inclination angle, okay, chip will not flow straight. Understand? Because there is some rake angle or inclination angle. So due to that, chip will not flow straight. Okay, it is coming something like this. So that is also helping the chip to curl. Okay, whenever there is some angle provided. Okay. Now, principle of forced chip breaking. So our chip is acting like a cantilever beam, and you are providing a height of H and a width of W on the cutting tool. So whenever this is coming and hitting this heel, this is called heel. So it will break here due to brittle fracture. So this is the principle. So this width and height will vary. Based on that, the chip size will vary. Understand? Now, there are different types of chip breakers. So first one is parallel step. So, okay, you are providing this kind of step on the rake surface of the cutting tool. And of course, flank is also involved. Simply a parallel step. So, and of course, we'll come back again. The second is parallel and curved. Okay, this is a parallel step, and there is some curvature at the end. That is second type. Now next is positive angular. So a step, there is some inclination provided for this step, and the width of the step is increasing towards the operator. Now that is positive angular step. Now width of the step is increasing towards the workpiece. So that is negative angular step. So another type is V groove. So actually names are interchanged. So this is not V groove. This is circular groove in this figure. This is V groove. Okay, this one is V. So circular means we are providing some some kind of arc, okay, shape that is cut on the tool, and here you are cutting some kind of V-shaped, okay, curve on the tool. Now let us try to understand these chip breakers. So coming to the first one again, parallel step is provided for general purpose cutting. Now what is general purpose cutting? So you are not cutting very hard materials and you are not aiming for very high surface finish, okay, etc. Only for workshop purpose, okay, you are cutting the work pieces. Okay, you are not going to use those components in very sophisticated equipment or machinery. Okay, normal general cutting. So in those cases, parallel step is used because parallel step is easy to manufacture. That kind of tool is easy to manufacture. It is cheap compared to the other types of chip breakers. That is the reason. Now, second is parallel and curved. You are providing little bit curves, okay, some small curve here towards the end. Now, this kind of chip breaker can be used for a bit of heavy cuts because you are providing a curvature. Okay, it can take now more force. Okay, if it is a sharp, then it will break easily. If it has curvature, it can take higher forces. So you can use this kind of chip breaker for little bit of heavy cuts. Now the other one is positive angular. Okay, here if you see the width is increasing towards the operator. So the chip, whatever is coming, okay, it is going towards the tool or the operator. Chip movement is towards the operator. And so when you want to protect your workpiece, okay, that means your chip should not go and hit the workpiece or it should not disturb the machining process too much. Then you will take the chip away from the machining zone in that fashion. So in that case, you can provide positive angular step. Now the other case is a negative angular. So here the chip, okay, suppose cutting, okay, at this location, it is in contact with the workpiece. Now it will go into the machining zone towards the workpiece. The curled chip is going towards the workpiece. So if you think that operator safety is more important at that case, or okay, workpiece need not be protected against the chip, okay, so in those cases you can go for negative angular chip. And there is one more thing also with these angular type of chip breakers, you can vary the depth of cut and feed. For different depth of cuts and feeds, you can use these angular chip breakers. Because so at this location, this is the width. At this location, this is the width. Understand? Here also it is varying. So if you slightly vary, okay, for a small range, you can vary the depth of cut and feed, and you can break the chips. But whereas for parallel chip, so you have uniform, even though your depth of cut is varying, the chip curvature that you are forming will not vary. Okay, there is no variation. So it is limited to, okay, a particular feed and depth of cut only. Understand? It will not work for different feeds and depth of cuts. And coming to the V groove, So you are providing one curvature on the cutting tool. So it is one way it is easy to manufacture this kind of groove on the chip. And coming to another, that is circular groove. This is V groove. This is circular. So V groove here, if you see the circular groove, the chip is coming here and it is going inside this and it is curling due to that curvature that you have provided. One thing is your radius of curvature for this groove should be less than, and of course it will be less than, the radius of curvature of the chip. Okay, chip is curling, so its radius will be more compared to the radius of curvature of this groove. That is mandatory, because then only chip will curl. Okay, so it is one disadvantage with circular groove is okay, large amount of chip is in contact with the workpiece. Okay, so it is almost in contact with the workpiece. So here if you are providing V type, so contact is less. Understand? So this is the one kind of shape. So it can be a little bit we'll say these are little bit easy to cut. Okay, generally this V groove or circular groove cuts are okay seen on the inserts. Okay, during cutting you will use some inserts for cutting purpose. We will see what are the different shapes of inserts, etc. Okay, later. So on these inserts, these kind of okay grooves are cut, because if you are cutting directly on the tool, you can have these things. Okay, these are favorable, but generally on insert these two are favored. So this is about the various types of chip breakers. I hope it is clear.
Hello, sir.
Yeah.
Sir, are these chip breakers are the modified nose of the tool tip?
Yeah, there are two types again. One is chip breaker will be directly cut on the cutting tool. That is one type, that is permanent type. The other type is okay, you will attach the chip breaker. Okay, there will be a slot for the chip breaker attachment on the tool holder. You will attach the chip breaker using some clamping or some welding also sometimes if you want a permanent type. Understand? Depending upon the application you have to choose. Is it clear?
Yes, sir. Then how should we so here in a V group and circular group, it's mentioned that V should have a negative rake angle, something like that. But how this cutting tools will be operated? Means parallel step and positive angular type, for example.
Operated means?
I mean, means how they will be hold, like what should be their rake and clearance angles for something.
Yeah, rake and clearance angles will change. Okay, because there is a cut here. Rake, okay, but this insert, whatever you have kept here, chip breaker, is very small. Okay, so overall rake angle will be different. Understand? Now, based on this step, the rake angle will change. Understand? Effective rake angle of the cutting tool will change due to the step type chip breaker. Okay, it will change. But we know that. We know how much angle okay is changing, because we know the dimensions of the chip breaker. Understand?
Okay, sir.
So based on that only you have to choose your parameters now. Your rake angle is changing. Now based on that, now this is entire tool including the chip breaker. So based on this only you have to set your cutting parameters. But these are not regularly used, this type of chip breakers. Okay, attached chip breakers. Generally, chip breakers are cut inside the these inserts. Cutting inserts are the tool like this. Okay, you are providing a small groove like that. You will not take a chip breaker separately and attach. Generally, you will not do that. Okay, it is directly cut on the cutting tool. Okay, let us see. Now, yeah, same thing now. Inbuilt chip breakers. So inbuilt means they are directly cut on the cutting tool. You are not bringing it, okay, a separate chip breaker and attaching to the cutting tool. Now, what are the characteristics? The outer end of the step or groove acts as the heel that forcibly bend and fracture the running chip. So outer end means the end which is away from the cutting zone. So one end is in contact with the workpiece, other end is not directly in contact with the workpiece. Okay, it will come in contact with the chip. So whenever it is hitting the heel portion of the chip breaker, it will try to curl, okay, and it will bend and break. And second is simple. It is simple in configuration, easy manufacture, and inexpensive. If you are cutting the groove for the chip, okay, you are forming the chip breaker on the cutting tool itself directly. You are cutting it, so it is easy. Okay, it is less expensive. So that is the advantage. Okay, if you are taking the chip breaker from somewhere else and fixing it, it is costly affair. You have to make some clamping or you have to do some welding for attaching it. Now that is not there here because this is already a feature of the cutting tool. So you need not clamp it separately. Now the geometry of the chip breaking features are fixed once made. So that is the disadvantage. Because you are cutting the chip breaker directly on the cutting tool, now you cannot vary it. If you are attaching it, you can take different types of chip breakers and you can attach it on that tool holder. One time you can attach the parallel step type. Other time when you think there is a need for angular type, you can attach it. Okay, like that. But if you are cutting it directly on the tool holder or the tool I will say, so you cannot change it. So that is the disadvantage if you are directly cutting. Now, effective only for fixed range of speed and feed for any given tool workpiece combination. If you are directly cutting it on the tool, so now your width and height are fixed. So it is only applicable for some small range of cutting parameters. If you are attaching different chip breakers based on requirement, you can vary the width and height and you can change from parallel to parallel with curve, or you can change it to those positive chip breakers, positive angle and negative angle chip breakers, like that you can vary. That option is there if you are attaching them separately. So here that will not be there. Now, whatever chip breakers we have seen earlier, they were mainly cut on the workpiece. Okay, or we have discussed here the inbuilt chip breakers. Now, other type is clamp type. If you are clamping the chip breaker. In clamping also, you can have fixed geometry chip breaker like this. There is a fixed geometry for the chip breaker here. You are bringing that chip breaker and simply clamping it. Okay, there is a hole drilled on this tool. So using a clamp, okay, like this, you are attaching this. Okay, once it is attached, it will have fixed geometry. Understand? So when you see the second one, we'll see the difference. Second one is variable width. So here you see, so this is the insert, carbide insert in this case. And on top of that, you are keeping a chip breaker. This is the chip breaker you are providing. Now you are clamping that with some mechanism, clamping bolt is there. Now here if you see, you can vary the step size, like, so currently it is here. Let us say it is fixed like this at one stage, okay, for one operation. After some time, if you want to change it, you can push it back little bit, or you can bring it little bit close also. Understand? So the width can be varied. So this is another type. So obviously here you can operate at a different process parameter range by varying the width, and sometimes you can vary the height also. Understand? So based on that, it is you can use it for various process parameter range. Here range is limited if you have fixed geometry, even though you are clamping it. Okay. But of course, the problem is you have to clamp it rigidly. Clamping should be clamping mechanism is a little bit complex. So that is the problem here. Is it clear? I hope it is. Okay.
Sir, one doubt, sir. Sir, in case of the step thing, there are two edges, no, sir. Which will be the principal cutting edge, sir? Like,
principal cutting edge is this only. This one.
and or can we use them interchangeably? Like one will be the principal cutting edge and the other will act as heel. Is it like that, sir, or only that particular edge is principal cutting edge?
It depends on the tool holder also. Okay. Because this total height and weight may be different. Okay. If they are same, even if they are same also, it is difficult to use them interchangeably. Okay. Cutting edge is fixed almost. Understand? One is cutting edge, the other one is heel. It depends on the tool, on which tool you are fixing this. Understand?
Okay, sir. Understand.
So here in the first case, this is the chip breaker. This is the insert. On top of that, you are fixing the this kind of feature. Understand? Now its width is constant. So that's why you are saying that this is a fixed geometry. So here, even though its width is constant, but you can move it in this direction. So it is a variable width. And definitely this is cutting edge. There is no doubt in that. Okay. Now the other form of chip that we have not discussed is serrated chip. So here serrated chip, it is also known as a non-homogeneous chip. So you will have sawtooth typed formation on one side of the chip. Okay. It is here see, there is a shearing taking place within the chip. But the chip is not completely breaking. So only some dislocation of the chip has been done, but it is not completely falling off. It is not completely breaking. Okay, it is a part of chip only. It is a one kind of, it is in between the continuous chip and discontinuous chip. Finally, it is coming like a continuous chip only. Okay. So this type of chip is called serrated chip. So we will see this kind of chip. And of course, let us see here. Semi-continuous. Okay, it is in between continuous and discontinuous. Chips with large zones of low shear strain and small zones of high shear strain. So that means, so at some location here, shear strain is very high. So that's why it is pushed away. Now in the in-between area, the strain is less. Okay. So if that is the case, you are getting the serrated chips. Chips have a sawtooth-like appearance. That is this one. This is associated when these kind of chips will form. This is associated with difficult to machine metals with low thermal conductivity. Difficult to machine metal means generally they are very hard, high strength materials. Okay, and they are heat resistance also. Okay, they have good heat resistance, and that means thermal conductivity is less. Okay, so when thermal conductivity of the workpiece is less, so it is difficult to cut those materials. Okay, because high heat is generated in the machining zone and it is not going into the workpiece also. So material ahead of the tool tip will not be heated up much because it is heat resistant. So it is difficult to cut them. Only at the cutting zone, due to friction and plastic deformation, very small amount of heat will be there. But okay, material ahead of it will not be heated up much. So it is brittle. So material ahead of the tool tip is brittle, and material which is almost very in contact with the tool is going into the plastic state. Understand? So now the chip is formed due to shearing action, yielding and shearing. That is one thing. And the other one is a brittle fracture is also happening simultaneously. Understood? Whenever, because the workpiece is brittle or hard, of course hard and brittle are slightly different, but hard materials are generally brittle, generally, not all. So chip breaking is due to, or the chip formation is due to brittle fracture because the material is hard. But the material which is very close, okay, or just in contact with the workpiece, at that location shearing is taking place again. So it is both, combination of both. So whenever that means the just a second. So at this location, shearing action is taking place. Or let us say we'll go a little bit further. Let us say we consider this. So at this location, whenever the tool tip was in contact here, so shearing is taking place. But material ahead will also try to, okay, that will break due to brittle fracture. Okay. So that is your tool is going inside due to some small crack. So that's why both are taking place. So because of that, this serrated kind of chip will form, and it will form for the difficult to cut materials like titanium alloy, nickel based alloys like that, and their thermal conductivity is low. So that is the reason, that is one of the biggest reasons. And yet high cutting speeds. High cutting speeds, why high cutting speeds? At high cutting speeds, you are not giving time for the heat to dissipate. Okay. So heat is not going into the workpiece and it is not softening the workpiece material, because chip is removed at high speed. See, you remember one thing, most of the heat generated during cutting process will be taken away by the chip. Understand? So once the chip is going away very quickly, heat will be, most of the heat will be left in the cutting zone itself. Chip will take small amount of heat. Okay. So that heat is not going inside the workpiece, because workpiece is heat resistant. So at some portions you will have shearing, because there is a high heat. So due to that, plastic deformation is there. But some portion of the workpiece which is ahead is brittle. So in that case, you are getting some thickness. So this combination will form these kind of chips, serrated chips. These are not regular kind of chips. These are formed for materials like titanium alloy, nickel-based alloy, okay, or some kind of very hard material, okay, high-strength steels like that. So is it clear?
Yes, sir.
So it is time now, 9:20. Okay, let us stop here. I thought I will start the other one also. Okay, let us stop here. So we'll discuss the next topic in the coming class. Yeah, any doubts in today's class? Or anything you would like to discuss regarding course also, you can discuss. Now very soon we will try to conduct a minor one. So all of you start your preparation. So obviously the first topic and these two topics mainly focus will be on these two. Tool geometry and the mechanism of chip formation.
Okay, sir. Sir, we will have on first week of February, sir. Mine.
What? Minor one.
Yes.
Okay, we'll fix the date. Of course, we have to consult the other section faculty and the students also. Okay, we'll see. But these are the topics. You start your preparation.
Yes.
Okay, so thank you. We'll close the session. Have a good day.
Thank you, sir.
Thank you, sir.